analysis of migmatites. So we go ahead with that.
So my first slide is to justify the analysis of migmatites and granites, and I put in between granitic gneiss. Probably you people working in India are very familiar with these terms. It's not so obvious in Europe because we have less of these rocks, even though they probably represent 20 to 50% of the outcrop of the surface exposure, but they've been a bit neglected. So I need to justify to study these rocks. And granitic gneiss, it's because I think there's, as I said yesterday, there is a difficulty to make difference between what corresponds to metamorphic rocks and what corresponds to plutonic rocks. And in between, well, if we don't know, put that into granitic gneiss, and that's all the pink. Most of the pink here is granitic gneiss, meaning that we don't know if they are metamorphic, plutonic, and whatever. It's an easy way out. And I don't know if you guys already mapped. At some point when you're mapping, you have your organization of lithological units, and there are rocks that you don't know where to put. You need to find a bin. Granitic gneiss is in an easy bin. And you can put most of the continental rocks into this bin. So, no need to justify, it's very important. And sediments that have been over-studied, I think, in Europe, it was natural because it was fairly easy to understand what was recorded in these rocks, in these sediments. Sedimentation that you can see with your own eyes happening today in rivers, on continental margin. You see what's happening, so you can relate to that record in the past that is recorded in rocks. Same for volcanic rocks. But for metamorphic rocks, plutonic rocks, it's more difficult to relate to something that is happening today at the surface, because it's not happening at the surface, it's happening at depth. Morning. But these sediments, they only represent, well, a small cover, a thin cover of a few kilometers at most, if it exists. The rest of the continental crust are these gneisses, migmatites, granites. So that's the most volumic important part. So I think that's very important to consider them in our studies. So what will the structural analysis of migmatites provide? So we'll see a bit later on the difficulty about studying the structures of these rocks. But what we're going to really get out of that is how they behave mechanically, the rheology of partially molten rocks and magmas that will come out of this structural analysis. It's really how they deformed, and then how they deformed tells us how they behaved in terms of mechanics. But then there's also another process which is related, that is recorded in these rocks, is, so migmatites, I should define them now. I'll do that later on, but they are made of a mixture. Migmatite is mixture of rocks. Of a white part that has a quartzo-feldspathic composition, a texture that we interpret nowadays as being representative of a melt that has crystallized, a silicate melt. And the gneissic part, that is the gray part, that has preferred orientation and a texture that reflects deformation before the presence of the granite. So it's a mixture. And we interpret this mixture as being representing a coexisting melt and solid in the rock at the time they were deforming, so partially molten rock. And as these two phases, the solid and the liquid, were coexisting, well, they could separate from each other, segregate. So the structural analysis of migmatites is going to tell us about melt-solid segregation. It's not a closed system. It's a system that is very complex. And then what we'll do is we'll jump scale, mostly tomorrow, and looking at what is the impact of partial melting that is recorded in the structures on orogenic evolution, and also on crustal differentiation, because this process of melt-solid segregation is the main process of crustal differentiation. Starting with a homogeneous crust, you end up with a differentiated crust in different layers. More mafic in the lower crust, felsic intermediate in the middle crust, and more granitic and sedimentary aluminous in the upper crust, where surface processes take over the magmatic processes. Okay. Well, we move from these ideas that were mostly motivating people to look at the relationship between magmatism and tectonics, and we'll go towards that. The first idea that motivated such studies is, well, maybe the way that, for example, lithospheric thinning would control melting by decompression of the mantle underneath. That's one way to connect tectonics, geodynamics, and magmatism. How tectonics will drive melting and magmatism. Another motivation was to say, okay, in places where magmas are in place, for example here in a Pluton, granitic Pluton in red, it might correspond to weakness in the crust and localized deformation. So the motivation was here to look at the relationship between magmatism and extension, localization of deformation. So move back a bit into history. So we saw yesterday the debate between Neptunism and Plutonism, with on one side people that thought that all rocks formed by crystallization of minerals in the Earth ocean, so a sedimentary origin for all rocks, and Plutonism that said that, well, but there are also magmas that are produced at depth. Good morning. And that and not all rocks are sedimentary. And much of the debate focused on the origin of granite. You know all granite, right? But does any one of you has seen a granite crystallizing? No. This is a concept. It's not an observation. Granite, its composition, texture is an observation. Granite being a magmatic rock, crystallized from a magma, that's a concept. Right? Nobody has seen that. This happens at depth. So this debate was very important, and it was natural. Now, we think it's obvious. We take it as a data, but it's really a discussion. So what were the evidences for granite being a magma? Because if we go back to this map, most of the granites are below sediments. So that was the first order observation of Werner and his team, is to see, okay, the granites and gneisses are at the bottom of our stratigraphic sequence. So they represent the first rocks that crystallized in the ocean. That was the logic. So what Hutton added, he said, but look at here in Scotland. Here are the sediments stratified. And the pink stuff is granite. It's not just underneath, it's cross-cutting. So that's the evidence for intrusion of granite into sediments. So in other words, it behaved as a magma that was flowing and cross-cutting the stratified sediments. So with relative chronology, that we know that now, we propose that this happened after deposition of the sediments, so it's not before. It behaves as a weak material, low viscosity. The next evidence was provided by Lyell. He said, but look at what happens to limestones at the contact with granite, with intrusive granite, they are transformed into metamorphic rocks. So granite also add some heat to the host rocks, and that's also one way to propose to argue for a magmatic origin for the granite. But then there was also this debate. Okay, is it all crystallized from a magma, or is it also metasomatic with the action of fluids that would help crystal growth? And this debate went on for the last century. And also then the relationship between granite and migmatites, per migma and ad magma. And it's here a drawing by a geologist, Reed, that proposed some artistic view of how magma would be produced in migmatites and then feed volcanoes. About 100 years ago, well, some guys reproduced granite in the laboratory. So they managed to melt a rock and then look at what happens when it crystallizes or cools down. Basically playing with the temperature. That's the temperature here, so it doesn't read very well. That's the original figure of Tuttle and Bowen. And Bowen, that's the guy who gives his name to the Bowen series. That all comes from thermodynamics, fed by experimental work. And here, for example, we are in the NaAl Si308, so that's albite, and KAl Si208, that's K-feldspar, orthose system. And so the composition changes in this axis, and the temperature changes here. And that's the melt. So that's the solidus. That's the liquidus, sorry. That's the liquidus. It's the line that separates the 100% melt from partially molten rocks. And what this guy showed is if we take a composition of a melt that is here, when it's 100% crystallized, it will give this proportion of these two minerals. But the first crystals to be crystallized will be on this side. And the melt composition, as crystals will crystallize, will evolve along this line. And the last melt drop would have this composition. A composition that is different from the composition of the early melt. So if this melt, this last drop, is separated from the crystals, then it would lead to something that is more potassium rich. And the residue would be more sodium rich. They did the same experiment in 3D, adding SiO2, quartz. And what happens is that, and this point is called the eutectic. Are you all familiar with this, with thermodynamics? Huh? And you can do the same experiments on the other way, by melting. And the first melt will have the eutectic composition. And then the melt will evolve until 100% of melting, and then you will reach the initial composition. So when they did the same analysis with the 3 poles, then they identified that the eutectic point has a composition that is close to the one of granite, halfway between plagioclase, K-feldspar, and quartz. And by making this reasoning about what crystallizes first and what is crystallizing at the end, this explains why K-feldspars are the first to crystallize, and then plagioclase, and then quartz in the interstitial space. So the next debate was about the room problem. If granites are indeed magmas that are coming from the lower crust, well, they represent today huge volumes. And if they were transferred through the crust, which place was it taken? Did the rock go aside? And how did it happen for this huge volume? One solution, so it's really led to a diversity of terms, which I'm not going to go through now. But there are different processes that were invoked. Diapirs, in mass motion of this volume of magma at once, or through dikes, small veins. And what is the link between migmatites and granite? So that would be the in-mass displacement of the full volume of granite. So this space has to be found in 3D in the crust during the transfer. Another elegant solution was to consider that not all of it moved at once, but was transferred through small conduits, small veins. Maybe not only one, but many of them, that would feed a volume of magma that would increase progressively as the melt would go through. In other words, that solves the room problem. That was a smart idea. And then in order to assess these models, and you need also to look at the deformation of the host rock at the place of magma emplacement, and see if the space taken by the magma is consistent with the space that is recorded by shortening in the sediments or in the host rocks. And also the timing. Was the granite also deformed at the time of emplacement, or is it post-deformation, post-structures, or pre-structures? So you need to construct these, so you need to take many measurements of foliation, lineation, and so on, inside the granite, outside the granite, and see how it looks in map view. So these are the general motivation. And now we're going to go into the definitions of migmatites. So the big book on migmatite is Menard, 1968, almost my birth date. And at first, migmatite was defined by Söderholm, a Swedish guy. No wonder, he was living in a craton like you guys, the Scandinavian craton, full of migmatites. So he was inspired by that. And he proposed a mixture of two genetically different constituents. One is intrusive relative to the other. To this group belongs the gneissic granitic rocks, see, gneissic granitic, which show net structure characteristic of incipient melting, frequently blind-ending veins, breccia-like granites with innumerable fragments of more or less completely dissolved older rocks, and finally stripped granites in which the only still preserved parallel structure indicates a faint remnant of the original properties of the rock. A lot of things, huh? A bin. You don't know where to put the rock, try to have a definition that is as wide as possible, then you probably manage to put your rocks into that. And I put in red all the processes that are involved. Intrusion, melting, dissolution, deformation. So lots of processes are invoked in that definition. Very, very complex definition. But in a way, after 40 years of working on migmatites, I see what he meant. Because it's that complexity that he wanted to represent. And a number of words have been also associated to describe migmatites: arterite, admatite, veinite, phlebite. Looks like you're going to the doctor. Diatexis, anatexis, palingenesis, metatexis, many terms. Again, this reflects the complexity and the difficulty to really understand what is happening. So if you're having trouble with migmatites, that's not a surprise. I'm still very puzzled when I go in migmatitic fields. It's very demanding. So these are all the migmatites that Menard described in his book: agmatitic, dictyonitic, Scholen raft, folded, stomatitic, surreitic, Schlieren, nebulitic. You can always find a friend when you're in the field. I think what is more compelling is this type of definition. And that's the one of Menard. A megascopically composite rock consisting of two or more petrographically different parts, one of which is a country rock, generally in a more or less metamorphic stage. The other, so that's the gneiss, The other is pegmatitic, apletic, granitic, or generally plutonic in appearance. That's the granitic part. So he added then this threefold definition: leucosome, melanosome, mesosome. Leuco is for white body, the lightest colored part of a mignotite, made of quartz and feldspar, with a magmatic texture. I think that's the key. Melanosome and mesosome is more difficult to really sort out, but it's made of iron, magnesium-rich minerals, biotite, amphibole, sometimes pyroxene. And the melanosome is usually surrounding the leucosome, and the mesosome is the intermediate between the two. So these are, I think, objective criteria to describe the mignotite. Myself, I use these when I describe mignotite in the field. And then he proposed these terms: paleosome, neosome, mobilizate, restite, resistor. And that all refers more to processes. So if I use these words, I use them when I interpret what I observe, not to describe. And that's something very important in the terminology, I think, is what's a very good example here. A terminology should be objective, based on observation criteria. But if the heterogeneity of rock doesn't allow to find easily the criteria to distinguish between rocks, then you end up with a very rich terminology, very complex. And it's not that useful. Let's take, for example, differences between different type of rock, of metamorphic rocks, mica schist and quartzite. We say, okay, 50% of quartz and above, it's quartzite. Below, if it's 50% of mica, it's mica schist. Why 50%, not 45, not, you know? Well, we take an objective criteria, 50%. Does that represent a process, an underlying process? We're not really sure. We probably know that if it's more quartz-rich, the sedimentary protolith was more evolved in terms of maturation and the separation between the different elements. If it's more mica-rich, it was more towards the clay and closer to the source or something like that. You know? So this relates to the process. So in other words, the terminology should help you go to the process, but it should not constrain you to the process. Like paleosome, if you use that in the field, you make an assumption not affected by partial melting. So you make the assumption that the paleosome, which usually in the mind of Menard is the mesosome, was not affected by partial melting. How come? You are there in a few meters, the PT conditions, which are the main parameters that are going to influence melting or not, and the chemical composition are not going to change so much. So there's no reason to keep a rock not affected, and just next to it, a rock that had the same composition, but then melt and solids were segregated. So I think these are risky. So we keep with these ones. But the idea is that from that analysis, then maybe we can assess whether we can propose a composition of a protolith, a rock that was before melting, and then identify which part was crystallized from the melt, and what was not, what was resisting from melting. Maybe some rocks did not have the right composition to melt, so that's resistor. And restite is the residuum after melt solid extraction. So when we look at this structure, very complex. It's no wonder why structural geologists didn't want to play with these rocks. How much of this structure is inherited from metamorphic rock before melting? How much relates to melt-solid segregation? And how much relates to deformation at the time the melt and the crystals were coexisting? These are the main questions we want to address. But before doing that, I'm going to go back into the basics of structural geology, so that we show that because I'm not sure you all had structural geology. You are teaching that, I guess? And not everybody. So the basic. So I think I said it yesterday, but it's very important for me is to distinguish plate kinematics, which is defined by motion of points far from the plate boundaries. So considering that the plates are rigid, not deforming. Plate tectonics doesn't work along plate boundaries because there rocks deform and the plate is not rigid anymore. That's why geophysicists said, okay, that's the complex zone of arc-like rocks. No? We don't understand. We cannot do plate tectonics in that. Plate tectonics is not about tectonics. It's about rigid motion. Tectonics is about rock deformation. So the name plate tectonics might be confusing. So we consider divergence, convergence, strike slip, plate kinematics. And then tectonics is about crustal deformation. Here the terms that I said yesterday that might be used with different meaning. Extension for a tectonics guy is when the crust is thinned. Compression is when the crust is thickened. And strike slip is when two zones of crust are moving relative to each other in the horizontal displacement, and usually by simple shear. And in between, you have all the cases between compression and strike slip, which is named transpression, and all the cases between strike slip and extension, which is transtension. And that relates, so when you try to relate to plate kinematics, usually compression is related to zones of convergence, extension to zones of divergence. Strike slip is like plates are moving on a horizontal plate, horizontal dimension. And in between, transpression is when the plate is moving relative to each other, but not perpendicular to the plate boundary, but with a slight angle. So it's oblique convergence, oblique divergence. And in between, it's normal divergence, normal convergence. But it's very difficult to retrieve from structural analysis plate kinematics. But you can, if you have the right structural structures. So structural analysis, well, we rely on the final state. What rocks look today, unless you do neotectonics, where you, actually I was sent this last night, movie that on YouTube, a guy filmed in direct the motion of a longer plate. Impressive. You can see the earthquake and boom. The first time I see that. Check on YouTube, maybe I can send you the link. So we look at the final state. So you guys know what the initial state looked like, because you probably know this type of cakes. Right? But if you didn't know the cake, how come you know it's the final state? It's because you have a mind idea of what was the initial state. And same yesterday, and we discussed that with the limestone. Because you're a geologist, you know that the limestones are deposited in horizontal planes. So you know when it's like this, well, it's been folded. But it's not obvious. So that's the initial state. So that's a cheap analog experiment. So we rely on final state. And structural geology is really a geometric analysis of structures with the aim of defining deformation state, reconstruct the deformation history from initial state to final state, and also by looking at the structures, we will allow to quantify pitting conditions of deformations. You don't have the same structures when the rocks are cold and when the rocks are hot. We saw that yesterday with the experimental deformation leading to fracture or to flow. And then, if we're lucky, we can translate this geometric analysis of deformation, shortening, lengthening, in plate motion and or forces causing deformation at the large scale. So the first step is, by looking at structures, identifying the strain ellipsoid. Reconstruct that. Where is the stretching direction, the shortening direction, and why is intermediate in between the two. So if you look at the fold like this, you have an idea of where the x direction, maybe the easiest one is to think about shortening. Shortening direction, you see where it is? Or here? in which dimension the cake was shortened. Horizontal. Horizontal. So if you say shortening, that's not enough. You have to say horizontal shortening. Because if material is preserved, then if it's shortened in one direction, what happens in the other direction? It's lengthening, stretching. So shortening in that direction, in which direction it is stretched? Vertical. You are a structural geologist. Same here. Shortening, horizontal dimension, stretching, vertical, and intermediate, perpendicular to the screen. So that's another confusion not to do. We have seen rocks that have been shortened. Yeah, it doesn't say much. You have to say in which direction. Because if there is deformation and mass conservation, then if it's shortened in one direction, it's stretched in the other one, perpendicular to it, by definition. So the next step is to relate this strain with the stress ellipsoid. The stress is the derivation of a force in one point and corresponds to a vector that we can subdivide in three main axes, sigma 1, sigma 2, and sigma 3. And this stress ellipsoid doesn't have to be parallel to this strain ellipsoid. So that's all the difficulty. And to make it very short, what I do to my students, I take a volunteer and say, okay, I'm going to punch you in the face. And usually there's not too many volunteers. But still, I'm just going to do it symbolically. And you don't know, at the time of the hit, when you receive the punch, then you feel the force. You know? But then, just shortly afterwards, you just feel deformation. The force is gone. And you don't know, just by looking at your face that has been punched, if it's been punched direct, how do you call that? Hook or uppercut. You don't know the motion, right? You just look at the final state. Right? In other words, so only when it's direct, that's what we call pure shear, then you can, it's what is the case of coaxiality between stress and strain ellipsoid, then there's not much rotation. But all the others, rotation of the deformation object. So when it's rotating, well, no way to go back to the stress ellipsoid, because there has been a rotation between the deformed object and the initial force that caused this deformation. And usually they understand. Okay? So don't talk to me about stress. Talk about strain. The only case where stress can be retrieved from strain is instantaneous deformation, very small deformation in pure shear. Three conditions that are not met in the deep crust. It's only met in the upper crust. So people are doing fault analysis, that works. And I'm not saying that we never can do that, relating the strain and stress ellipsoid. It works for fault analysis and faults that have not been too much folded, rocks that have not been too much folded. So instantaneous strain, small strain, and pure shear. This I'll skip. So that works on the upper crust. But anything below, where you have a component of non-coaxial deformation, in other words, there is rotation of the strain ellipsoid relative to the stress ellipsoid, and structures cannot be used directly to retrieve stress. We try, but it's difficult. So you have different type of structures, schistosity that appears in the axial plane of folds. These schistosities are usually transposed in other schistosities. You have complex polyphase folding and the superposition of structures. So that was very brief introduction to structural geology, but just to give you a sense of the complexity and why it was neglected, this part, because it's not following the rules of continuum mechanics. Deformation is not infinitesimal, is not instantaneous, it's probably not pure shear. So all these were defined to decipher the structures in the upper crust, and all these do not work in the lower crust. So how are we going to do? Because we want to move and improve the structural analysis of these rocks. Well, maybe the next step, I was asked that yesterday, I think, maybe, I'm not sure who asked me that. No, you asked me about the field of structural analysis, where it's going. I think so structural analysis really relied on continuum mechanics. The next step would go, if we want to understand structures in this type of rocks, that were probably two-phase rocks with liquid and solid, we need to move to fluid dynamics. And probably in these rocks, we can probably find structures that record laminar flow, turbulent flow, and so on. Fluid dynamics, not continuum mechanics with infinitesimal deformation. We're not there yet. So my first contribution to that, we were several researchers working on that during the 90s and 2000, was to look at the mineralogical composition, texture, distribution, proportion of granite and gneiss, and looking at the structures, measuring all sorts of things, and proportions between granite and gneiss. That's very important. And in order to improve, what I did is I read a lot on geometry of melt-solid system, rheology of partially molten rocks and magmas, experimental work, conceptual work, theoretical work, melt crystal segregation, partial melting, fractional crystallization, melt magma migration, and metasomatism. So that's fed my brain to then be able to find things that could relate to all these processes in the structures. So the geometry of two-phase system. So in the following, I represent the gray represents the gneiss, and the yellow the silicate melt. So that's conceptual. So at first, the first melt drop will occur between grains and be isolated from each other. So if they are isolated at the grain scale, they cannot connect, they cannot migrate. So at this scale, grain scale, the system is closed. All the melt is preserved in the rock. And as melting proceeds, the volume of melt increases, and at some point, the melt will connect. The small pockets will connect to each other, which controls the ability to migrate from one place to the other at the grain scale. So that's what's called liquid connectivity. It's the first percolation threshold. A percolation threshold is used in any type of science, not only geology. And then if the melt increases in volume, there is a second percolation threshold, which corresponds to the solid continuity. Believe me or not, but in the 90s, structural geologists started in 2 dimensions. They looked at that in 2 dimensions, not looking at the top of that diagram. And they identified only one threshold. Because in 2 dimensions, it's either the solid is connected or the liquid is connected. Structural geologists. And geologists are not good at physics. And so at first, they started like that. So they managed to distinguish only 2 types of migmatites. Or actually, migmatites and granite. But in 3 dimensions, I can have my left hand with fingers connected. That might be the liquid. But the solid still connected around. That is my right hand. And at some point, up, the solid might disconnect. And that's the second threshold, whereby solids are floating in a liquid. And this is, so that's locked melt migration at this scale, at grain scale, and this corresponds to the transition from partially molten rocks to magma. And in magma, the solid might settle in the liquid. So it's a different process of melt crystal segregation than percolation through grains. And these thresholds might, if the magma has been separated from the solid, or at least partially, then the magma might take place somewhere else, and this threshold will be crossed in the way back during cooling and crystallization. So at some point, some crystals might be separate to each other in the magma during the initial step of fractional crystallization, and then the crystals might start to touch, form a continuous solid framework, but the liquid might still migrate through this framework. And at some point, the framework will be so dense that the liquid will be trapped in small pockets. And that's the final texture of the granite that I showed you with feldspars, plagioclase, and quartz. The last melt drop is composed of quartz. So what is controlling melt migration? The geometric condition first is what is called the dihedral angle, which is the angle at the interface between the liquid and the crystals. And it's thermodynamically determined by the tension force. If you look at your water in a glass, if you look at the interface between water and glass, you see that there is an angle. It's not the intersection is not 90 degrees. It's an angle. And it happens that for minerals of the continental crust, for felsic rocks, the dihedral angle is below 60 degrees, which allows the melt to be connected for a small amount of melt. If it had been greater than 60 degrees, then the first melt pocket would have this shape, and it would require a lot of melt before connection. So in practice, for about 10% of melt in partially molten rocks of felsic composition, this connectivity is reached. So only 10%, 5 to 10%. For on the other side, crystal aggregation is also controlled by the geometry, the shape of the crystals, and the more compact they are, the more crystals is needed to ensure a connectivity between them. If they are very elongated compared to their thickness, then they might contact for low crystalline proportion, right? So it's the same. What are the driving force for melt crystal segregation? Well, the first one is viscosity. The viscosity is the ability of material to deform under stress. And the liquid has a low viscosity compared to the solid, so will tend to migrate into dilatant spot where there is decompression, and that's related usually in the rocks to deformation. So where the rocks will dilate, the liquid will go into it. The other force that we can invoke is buoyancy, related to density inverted gradient. And usually a liquid, well, it's not true in all conditions, but usually at crustal conditions, the liquid is less than the solid that it comes from. So they tend to segregate by buoyancy. But if we take we are sitting here on top of the Deccan Trap, or close, right? Deccan Trap is made of basalt. Yeah? Basalt, what controlled its emplacement on top of the Indian continental crust, do you think? Viscosity or buoyancy? Basalt is more dense than granite, even when it's liquid. So it's viscosity. It's the weight of the Indian craton that pushed on the magma that was produced underneath, and when it cracked, the liquid went up. Just by viscosity, not by buoyancy. Surprising, no? So melt migration, we saw percolation, that's migration of liquid across grains that are forming a continuous solid network. But there's also the possibility of fracturing, rupture. It's usually when there is a strong thermal contrast between the melt and its host rock. So it's not happening usually at the place where melting occurs. Segregation by percolation is happening probably at the place of melting. And then there is also the in-mass motion of magma by diapirism, which is driven by gravitational instability. And the crystals might accumulate in the magma. So all these are the processes and forces that can control melt-solid segregation. the density of melt and rocks when they have been separated to each other. So if we take here the density and the melt percentage from 0 to 100% melt, what happens? So I represent here the liquid conductivity below 10% of melt. The solid continuity, according to the different geometric possibilities that controls this continuity, is probably between 20 and 60% of melt. Usually we take 40% as being a good average, but it's very heterogeneous. So if we take the density of a gneiss, it's usually here. Amphibolite is a bit higher density. A gneiss made of quartz and feldspar, it's here. And the melt, granitic melt, is on this side. So it spreads over a wide range according to its composition, but it's usually less dense, not that much, but less dense than the gneiss. So what happens at the liquid conductivity when the liquid segregates from the gneiss? Well, the residual solid will be, so the liquid will go, its density will resemble this one. And if it's extracted, then the residual gneiss will increase its density. And if you think about it, if segregation at this stage is efficient, well, the migmatite should never have more than 10% of glucosome, which is not what we observe. So what we observe in the field is that sometimes migmatites have more than 10% of glucosome. So that means that this drainage was not very efficient. So it allowed the melt volume to increase, reaching the solid continuity threshold. At this stage, its segregation will occur by accumulation of crystals in the magma, and the residual accumulated solid would have a density that is greater than the liquid. So you see that melt solid segregation will increase the difference in density between melt and crystals. So now in terms of rheology. So here we represent the strength of the rock in megapascals, and same here as a function of percentage of melt, with the same threshold, liquid conductivity, solid continuity. And what experimental work shows is that for rocks that have not too much melt or no melt, they are very resistant, and as soon as there is a few percent of melt, there is a decrease in 1 or 2 orders of magnitude in the strength of the rock. So the presence of melt will weaken the rocks. And then there is a catastrophic drop of strength by 4, 5, 6 orders of magnitude at the transition from partially molten rocks to magmas. But this is a log scale. So the first 2 orders of magnitude are very important. These look in log scale much more important, but you go from here to 100,000 to 10,000. So that's a lot. And this is represented in the few next slides in different scale, but here we can see that there are 2 thresholds. The first one is decrease in viscosity at the solid partially molten transition, and that probably leads to crustal scale strain partitioning, localization of deformation into weak zones. And within partially molten rocks at the contact of magmas, then there is another loss of strength that might be controlling gravitational instabilities within partially molten layers. And we come back to that later. So that's another representation of that thing, but in a linear scale. So in linear scale, the first drop is here, and the second drop is here, but it's not even seen at this scale, because it goes from 1 to 0.1. So you have to take a loop there, and in order to see that second threshold. So you see first one and then another one. So that's just playing with the scales, actually. Yeah? It doesn't show the same thing if you look at the log scale and if you look at linear scale. But I'm not going to go through that much more. Just remember that the presence of melt will weaken the rocks, and if the transition from partially molten rocks to magma is also associated with more weakening. Are you okay so far? I didn't ask actually if you had questions relative to yesterday. Now break?
No, we can take them in the break. We have about 10 minutes.
Okay. So now, metatexite, diatexite transition. So that's, now we're getting into analysis of structures in migmatites. So I thought, looking at the diversity of terms defined by Mehnert and the others, maybe what is really important is leucosome, mesosome, and look at the relationship, geometric relationship. And this allows to distinguish between two different types of migmatites, the metatexites and the diatexites. That's much more simple, no? Rather than to have 15 terms, 2 terms, metatexite on one side, diatexite. The metatexite defined by a continuous gneissic foliation, which is marked by alternation of mesosome, leucosome layers. And you see here in this example that there are 2 superimposed layering. You see that? Darker here, gray, more gray here. What might, and then, so that's the meter scale. Lost the scale here, but there was a notebook somewhere here. That's something like 1 meter scale. And then within the darker, there are alternation between leucosome, mesosome, at a 10 centimeter to centimeter scale. Within the gray, there's also leucosome, mesosome, second order layering. What might these represent?
Segregation of minerals.
Yeah? Which one? Which layering what represents that?
So the white bands are fixed.
Yes, the leucosome, mesosome. Huh? I think that's my interpretation. What might represent the other layering at the middle scale? This might be a inherited banding from the photolith. Maybe more quartz-rich sediments and more clay-rich, mica-rich sediments. Metapilite, metagowaki. And both of them would melt, and you have a superimposed layering on top of that photolith layering. So that's one way to retrieve 2 different information, the history of the rock before melting and the history of the rock at the time of melting. But again, what I just said is interpretation, but you rely on the description of the rock. You have banding at the meter scale and then layering at the centimeter to 10 centimeter scale of leucosome, mesosome. Make your description correctly before the interpretation. So that's an example of that. That's my PhD thesis field area. And you see here the continuous, or more or less continuous gneissic framework, and the foliation that is defined here as the synmigmatitic foliation marked by leucosome, mesosome alternation. And you see locally, this leucosome is concordant to the foliation, and it shows also in the mountains. That's one of my best pictures. So I was taking the picture like we used to do, you geologists. We look at rocks like this, take pictures, and all of a sudden I had some wind, and boom, I saw the mountains. I said, wow, I see the structures in the mountains. And this made the cover of Terra Nova. I was presenting that at the oral presentation, and the editor of Terra Nova was in the room. I said, I want that picture for the cover of Terra Nova. He didn't care about the paper. He said, but I want that picture. Okay. And see that locally, the leucosome that is concordant here, up, is discordant. And my interpretation is that here you have a dilational zone that corresponds to boudinage, stretching of the gneissic foliation, that opens a dilatant spot into the melt, which will control the migration of the melt into it. And you see also a fringe of darker minerals, that's the mesosome, the melanosome around the leucosome. And that most probably reflects back reactions, retrogression, at the time of leucosome crystallization or melt crystallization. It will release water. and will promote reaction in the host rock. So that's really, I think, telling us that this melt has crystallized and was produced here. It didn't come, it was not intrusive from very far. Diatexite, made of granite with very heterogeneous texture, full of enclaves of different sorts. You still see sort of a preferred orientation that might reflect orientation of solid bodies in the magma at the time of magma flow. So technically, this corresponds to a granite. No, most people would call that a granite. And you cannot blame them from that. But here, with the heterogeneity of and the richness in enclaves, I think it's more pertinent to talk about the diatexite, which is really part of the mimetites, because it probably reflects the fact, and we'll see that with field examples, that this magma didn't move very much from its source. So it's really the field scale relationship that tells you if you should call that a granite or a diatexite. And we see that in examples. And that's here for the same field area. The first picture was taken, this picture is taken to the left of this one. And here we have the metatextite, diatexite transition. And it's made of a place where you see very complex structures. So it's the partially molten rock magma transition here. And we see that relationship between metatextite.
Those small enclaves there, are those garnets?
There are garnets, not probably in here, yes. Yeah, you see garnets in these rocks here. These are mostly metapelites, and you see, you can see the full metamorphic gradient, and that's a very good argument also. It's for having these rocks not be moved too much if they are preserved into their metamorphic gradient. And you can map in this region all the azograds from biotite, chloride biotite, and then garnet, and then staurolite, and then sillimanite, and then sillimanite with leucosome. That's also very important evidence.
In which of these types you will find stigmatic folding?
Stigmatic folding, probably in these ones. Yeah, there's been much. Stigmatic folding, I think, it will tell you about the contrast in viscosity between the leucosome and the mesosome, and probably also it's controlled by the thickness of the leucosome compared to the thickness of the mesosome. Okay, so now that's the first order structural evidence. So now how it looks in microstructures. And that was even more difficult to address because, well, when we do experiments, you can quench the experimental molten rock, and then the melt will transform into glass. But first, these rocks were probably exhumed for more than 15 kilometers depth, 20 kilometers depth to the surface, and it took several million years. So this glass is no longer there. It's crystallized into quartz, feldspar. So it's difficult to distinguish because you don't see the glass. But still, if you look at it carefully, you start to find these textures, and especially the dihedral angle that is below 60 degrees, that is identified here in experimental work. You find them here. That's an example of interstitial feldspar in the quartzite, and you see these textures, they look very similar to that. So here we can propose that the feldspar was crystallized from a melt into a quartz-rich rock. Because rocks that are metamorphic and coming from more than 20 kilometers depth, usually the texture, microstructure, looks like that, with angles between here quartz crystals at 120 degrees that reflects reequilibration according to the tension force, at the surface tension force. That's like a tension force. Everybody's familiar with that? If you take a soap bubble, its shape is spheric. If you put bubbles together, they start to agglomerate, and the shape will be, if you make a section to it, it will be hexagonal. That's this shape. And that's controlled by the tension force, surface tension force. Yeah? So driving force here, so that means that these quartz that probably started being sandstone. So in the sandstones, the quartz grains were rounded. So the quartz grain boundary migrated under that force, that tension force. So these are not fractures, these are grain boundaries. Okay? So this is true for quartz. It's true also for amphibole. Amphibole, that's not its euhedral, it's not its crystallographic shape. This is controlled by the tension force. And if you take plagioclase and amphibole, same, in the interface between these crystals, you will end up with, if it's been deformed under high temperature, we'll end up with a texture like this with 120 degrees grain boundaries. So, to find textures that preserve the melt crystals coexistence, you need to really seek for it. This is a very good example where you have a K-feldspar film around plagioclase and quartz. So most obviously this crystallized from a melt. And in other places you have these 120 degrees angles that are preserved. Same here with microclean, making a film around biotite, quartz, K-feldspar. So that most probably also was a melt film that crystallized, and it's been preserved. It's not been recrystallized. Another example with quartz. And here it's interesting because you have quartz and plagioclase. What might be the status of this plagioclase? It looks fairly euhedral. So my interpretation would be to say that also this plagioclase crystallized from the melt with the quartz. And probably this plagioclase might be residual from the rock that was molten. So then we start to point out, in these complex textures, which crystals are residual from the melting reaction, that were the reactant, and which minerals crystallized from the melt. And it's not obvious, If we look at that macroscopically, it's difficult to distinguish between this plagioclase and this plagioclase. And actually, I probably made a big mistake. I tricked you, but I'm going to suicide myself structurally. I think this was a big mistake. It was useful, but I took that criteria, and luckily I took a criteria that is objective in the field, continuity of the foliation, discontinuity of foliation, to distinguish between partially molten rocks, metatexites, and magmas, diatexites. I should say that, but I'm going to say it because I'm a honest person. By saying that, you say that all these rocks came from a magma. And this, for the Velay dome in the French Massif Central I showed you yesterday, it's 100 kilometers, so it's 3 times the thickness of the crust. So I said it's a crustal scale process. The implication of that would be that probably half of the crust was magma. We haven't identified that with geophysics. So I probably made a mistake by calling that diatexite to granite. So coming back to what I just showed you, how much is this plagioclase and feldspar residual from the previous rock, the reactant of the rock that was undergoing partial melting? How much of this plagioclase, probably K-feldspar, crystallized from the melt? Probably not 100%. Probably half of it is residual. And that's the field of research I'm investigating now, is looking at these rocks, trying to identify texturally, chemically, crystallographically, which one are the reactant, which one are the product of the crystallization of the melt, which one are also, there are also other crystals that do not talk, this is probably more for the master students, the peritectic minerals. The one that crystallize with reacted, that are the product of reaction with the melt. But they never been crystallized from the melt. They are solid. So that's the next step. But let's continue. So these films might also form what we call granophyre or myrmeckite, which are really intergrown K-feldspar and quartz for the granophyre, pleasure clays and quartz from the myrmeckite. It's difficult from the eye, even with a microscope, to distinguish the two. Other type of myrmeckite or granophyre, forming films around crystals. Same. So let's move back now to the macroscopic scale. So these textures, and here you see the garnet, and around garnet you see the leucosome. This was also my field area for the PhD, and I was very pleased to see limonite that big. Didn't need a hand lens to see them, because I'm not a very good petrologist, so I'm happy when the minerals are big like this. And here you can see that it looks like an eye. So the garnet is surrounded by leucosome. So that's a good evidence, I think, to call upon a peritectic garnet that was formed as a reaction, as a produce of melting reaction with the melt. So here in that, this is all the result, that was the product of the melting reaction, but only the quartz and feldspar, and probably not all of it, crystallized from the liquid, and this was a solid product. And you see that here, this underlines the foliation. So this process that occurred at the grain scale is already the result of segregation of all the liquids forming at the grain scales to form these leucosomes. That corresponds to the first migration by percolation. In other words, this didn't form here. This melt didn't form here. It formed in this rock and was collected at the grain scale by percolation during deformation. So this foliation is not inherited from the protolith. This foliation is recording the process of deformation during melt segregation at the grain scale. So the semi-magmatic foliation reflects melt segregation coeval with deformation. Melt might also migrate into budins. When you have more resistant layers, they might localize deformation, whereas the other ones that are weaker will be continuously deformed, and these spots will drive melt segregation.
Is it okay to call it a budin?
Yeah? No? Yeah, budin? No? The definition of budin is that you have initially continuous layer that is stretched into several parts.
So you can call it a budin?
I think so, yeah. I mean, that's what I do in the field. You have here leucosomes that are both folded and also in the axial plane of folds, another sites, structural sites of melt segregation. See here a series of pictures of leucosome, mesosome, and a small rim of melanosome. And that reflects also probably, and you see there's some sort of repetition between leucosome, mesosome, and that's something that probably tells us something about the physical process. Say another example. So I'll skip that. And you say, Malika, I should almost close, huh? Okay. So, yeah, we used the asymmetric distribution of leucosome relative to the gneiss to infer polarity of melt segregation, melt migration. And I think what works very well is, you see here there's the leucosome, the same here, leucosome, that, and here budinaged layer that is more competent, and you don't see leucosome on the other side. So there's leucosome only on one side. And this we interpreted as, that was my master degree, interpreted as being related to migration of melt that was stopped beneath a mechanical barrier. And that, in other words, will be used to tell the polarity of migration. And it was funny because at the time, everybody thought that granite melt would move upward. But when we said this is a polarity structure, I said, wow, how do you know? I don't know. But I could find that this distribution of asymmetric distribution of glucosome relative to gneiss is consistent at the regional scale, and it's always gives the same polarity. So I think it was very compelling. Another type of polarity structures, these what we call cauliflowers. You see one side of the glucosome vein is fairly straight, parallel to the foliation, and the other side is sort of rounded and is discordant on the foliation. And we took that as being evidence of small diapias. It also tells you the polarity. So we saw melt segregation to form concordant veins at the grain scale, but then these concordant veins might connect to discordant ones. As very often as we see that. Well, basic structural geology will tell you that this cross-cutting is later than this. But the textural continuity of the leucosome from here to there, I think I would interpret that to be magma at the same time, and then crystallize from the same magma. And actually here you see a diffuse relationship between the leucosome and the mesosome, whereas here where you have a more quartz-rich rock, then here it's very sharp. This is intrusive. This is not intrusive. This is extraction. And you see the cordiorite, that's not garnet, that's cordiorite. Cordiorite is found in leucosome concordant and also in the discordant ones. So it's another evidence for having the same melt being concordant to the foliation discordant. So this also is contemporaneous with deformation and opening of dilation sites. And usually concordant leucosomes are found for less than 20% of leucosome in a rock, and as soon as you reach more than 20% of leucosome, then you have this concordant-discordant relationship. So another place where it was wonderful to study this transition from metatexite, continuous framework with concordant and discordant veins, to diatexite, enclaves into heterogeneous granite, is Namibia. And here it was very compelling to see that metatexites are always on top of diatexites that are diatexites in the core of large-scale domes. So I think this also gives us a continuity and the increase of amount of melt, maybe not partially molten to magma, but increase of amount of melt going downwards in structural section. And for the, I mentioned the diapias. It was not very famous, you know, popular. In the 90s, people thought, okay, diapias, that's old geology, doesn't work. In the field, the melt only migrates through dikes. Well, here I had one of my geological ecstasy, and we were walking along a trail, and we saw that, you know, in two migmatites, you see the structure of migmatites like this, and you see it's going like that. And that's caused by more granitic rock. Well, I'm not sure if you see the same thing as I see, but these diapias, they tend to form mushroom shape. I see half a mushroom here, but I'm very fond of looking at mushroom in the forest myself when autumn comes in France. So I have the eye for mushrooms. So this is half of a mushroom. So diapias exist. Maybe not in the upper crust, but in mid to lower crust. Well, you find this not that often, but it's the more you look for it, you'll find them. Do I have time to do some physics? Short?
Maybe you take a break and come back.
It's not good, because that's after it has nothing really to be related. So I'll be very short. So this might be represented by what is called the compaction theory. It's like if you take a sponge with water in it, if you push on the sponge, the liquid will segregate by percolation, and there is some kind of repetition or frequency of that compaction. It's called the compaction length, which is related to permeability and viscosity of matrix, viscosity of fluid. And it's been shown that it could be one way to explain this repetition of leucosome mesosome. And both for concordant and discordant ones, this is also kind of compaction theory. Veins might also form according to shear bands and localize also folds. So I'm not going to go through that further. We can build the same story for the crystallization. And if you have contacts between two different types of granite, for example, leucogranite and granite with phenocrysts, well, you see that here some of the phenocrysts are also, so it's, the boundary is not like a sharp one, intrusive one. So most of the phenocrysts are here, but some are floating in the leucogranite. So I would take that as an evidence for accumulation of crystals rather than having two different granites. It's the same, but most of the crystals are here and the residual liquid is here. Of course, it will affect the chemistry because the minerals are different, but it doesn't mean that they were coming from a different magmas. It's the same magma. Same here. Same here with accumulation of garnet in the first part. That's Ukraine. Was in Ukraine in 2004 or 5. It was a time at Soviet Union, you know, fell about 10 years before. It was kind of floaty. The ambience was floaty. This is close to, it's in Donbass. And uranium mines everywhere. So we'll talk about that on Thursday on the talk about social impacts and social challenges related to mineral resources. There's no surprise that the Russians went there first thing, right? And I'll leave you with questions. Here's an example, a fantastic outcrop with migmatites, very heterogeneous, and you have here an enclave into a diatic site, and within that enclaves, different enclaves into enclaves. Wow, that means that's a very dynamic process. You had enclaves and then crystallize in some kind of a partially molten matrix, and then this enclave was then re-put into dynamics into a partially molten rock. So this means that these processes are very dynamic. Dikes in dikes, two dikes that are separate from each other, and then up, they become the same dike. We saw that yesterday with DPEC, of multiple intrusions. So it's not always differentiation of the same magma. It might be one magma that comes into another one. Same here, up. And magma interactions, magma mingling between a mafic magma and a felsic magma. I think I'll stop with that. No, I'll skip the Pluton and have a conclusion. Okay, that's my conclusion slide. So melting starts at the grain scale with small pockets, and probably where all the minerals that are required for the melting reactions are connected to each other. So in other words, K-feldspar, quartz, biotite, if you have biotite dehydration melting, and then will lead to formation of small melt pockets in between grains. When these are connected, they will feed. This will not be really identified at the macroscopic scale. You need to go at the microscopic scale to see that. And the only evidence for melts, the presence of melts, is when you start to have melt segregated in leucosomes. So it's already 10% of melt. When it's less than 10%, you don't see it in the field. And then beyond 20% of melt, of leucosome, you start to go from concordant to concordant-discordant veins. And that's probably the process that is required to have migration of melt out of the outcrop to feed plutons higher in the crust. And that's if the melt is well drained out of the rock. If it's not the case, then the melt will accumulate. We go beyond the metatexite-diatexite transition, and then you have accumulation of solids into the magma. And this will lead to crustal differentiation, so that was my mistake, magmatic zone here. Maybe I need to refine that. Accumulation zone at the bottom, partially molten zone, and intrusive zone that corresponds to the magma that has migrated out of its source and being intrusive in colder rocks. Okay, let's take a break. But you can ask questions if you have more now. Yes? So everybody's ready? So now let's move to, so we went very basic concepts and definitions, structural analysis. Now let's move to field examples with the Alpine Himalayan belt. So that's a topographic view of the Alpine Himalayan belt from Gibraltar all the way to Tibet and Indonesia, going across the Alps, the Taurides in Turkey, the Zagros, and so on. And you see very different topographic features. The wedge shape, triangular shape mountains in the Western Alps. The Himalaya Tibet represents a plateau, flat plateau, with an altitude average 4,000 meters. And the Aegean, wow, where are the mountains? There's a hole in the mountain here. That's going to be a big question. How come in a zone of plate convergence there is a hole in the mountain? And these topographic features formed in the same kinematic environment. There are some slight differences between because of transfer faults, but roughly speaking, it's related to first opening of the Central Atlantic, North and Central Atlantic, and then opening of the Southern Atlantic, which controlled the eastward first motion of Africa, or Gondwana, because there was also India with it at the time, and Arabia relative to Eurasia, and then a more northerly trend, starting somewhere between 90 and 80 million years. And that corresponds to the opening of the South Atlantic. And roughly speaking, how is the mountain belt? What are the first order characteristics of this mountain belt that you can see its orientation, width, thickness, or altitude? Well, it's roughly east-west trending. Is it logic? Yes, because with a north-south motion of Africa and India, you would expect a mountain belt that corresponds to collision and shortening in the north-south direction, and therefore an east-west trending mountain belt. We'll see that in the details is much more complex, but first order, that's correct. Its width, is it equivalent throughout from west to east? Well, no, it's much wider here than here. What does that reflect? Well, that reflects the scissor shape motion relative to a pole, an axis of rotation that was further to the west, northwest here, and Gibraltar is much closer to the axis of rotation than Himalayas and Tibet. So there has been, even though the vector of rotation, angular velocity vector might be similar or close, except that it's different here for India because it's been separated from Africa. The linear amount of convergence is much less here than here. So you expect a much wider belt here than here. That makes sense? And also, thicker crust and higher topography here than here. First order, it makes sense. So we're going to go through for today and tomorrow, and even, no, today and tomorrow. Tomorrow. I even Thursday morning. Through different examples. The Alps, which represents an orogenic wedge, triangular shape. Tibet and Himalayas, mostly the southern part, which represents an orogenic plateau. And the Aegean, the hole in the mountain belt, that represents an intermontane basin, a collapsed mountain belt. Well, so let's start now with the general picture of the Alpine Himalayan belt, its constituents and the kinematics and the structure at depth. So the main continental blocks were identified by Argan, always the same guy, was very productive. He published only 2 papers in his life, but very influential. One on the Alps and one on Himalaya Tibet. And you can see here all the cratons, the East Africa, Arabia craton, the India craton, Scandinavian craton, Siberia, and all these are the blocks that are moving relative to each other to form the Variscan belt and then the Alpine Himalayan belt. That's a wonderful map. Huh? So a more modern version of this, still see here for Western Europe, Scandinavia, and the northern part of Gondwana, and also the northern part of Arabia, and the Variscan belt and the Alpine belt. So basically, the Variscan and Alpine belt formed around the same, or in between the same blocks that went up and down, up and down. So that's the same type of map looking towards the east with the same blocks and the different Variscan and Alpine belt. So plate kinematic reconstructions were done looking at all the geological record, mostly on the 2D. It's a 2D perspective. It doesn't really account for the subductions. But subduction is here identified by high pressure rocks or tectonic accretion of sediments. Actually, these reconstructions mostly rely on sedimentary rocks. So that's 230 million years ago, at a time where Pangaea was still forming one continent, and you had Neotethys, Paleotethys, so that the old ocean, Neotethys, and you recognize the different continents here. So Europe, Africa, Arabia, and Siberia here, and the future Himalaya, Tibet here. So you had the accretion during the Indocenian phase of the Tsongpon Ganze terrain. That's forming the northern part of Tibet. We worked with colleagues on the eastern part of this terrain. And then the start of opening of the central Atlantic, that will start to have Africa moving this way, and opening small oceanic basins in this area at the same time as this one is closing. And here there's a huge Neotethys ocean. So we start to open the central Atlantic, and all these small basins in between Eurasia and Gondwana, and the continental ribbons in between that are going to be the ones that are going to be technically accreted afterwards. So let's play the movie. Get a sense of the motion? Opening of Central Atlantic, closing of smaller. So as the South Atlantic opens, then all these small oceans will start to close. That's the same ones that were opened during the opening of Central Atlantic. And here, India, for some reason, that is something that is also not very well understood in terms of dynamics, separates from Gondwana, and then very rapid convergence towards Eurasia. And that is marked by the Himalayas and Tibet. We do not want to forget Tibet. So we have, during that story, opening of oceans and tectonic accretions of continental ribbons. That's the current day plate kinematics, where it's remarkably consistent with the one that has been recorded for the last million years. So it shows still convergence of Africa, Arabia relative to Eurasia fixed, and India also converging towards Eurasia. I won't say much more about that at this time, but it's remarkably consistent. But at the same time, you have motions like this here in the Aegean domain. Gibraltar is going like that, Calabria is going like that. There are some complexities. But the first order in terms of blocks, that's why I'm saying it's important to look at the motion of blocks far from the deformation area. And that's plate tectonics. When you look at in the deformation zone, that's much more complex. And that's not plate tectonics. That's different. I will see the details on it just later. Seismic activity. So here it's a different picture, and you see better. So we see the shallow earthquakes, the orange ones, the ones that are crustal, less than 30 kilometers. But we see also the deep earthquakes from Gibraltar, Calabria, Aegean domain, the Taurides, Zagros, and also Himalayas. You have deep earthquakes everywhere. So subduction and collision at the same time. Crustal deformation and lithospheric deformation at the same time. In terms of topography, so the current topography for Europe is, we see the Alpine, the Western Alps, and there's a hole here, Pyrenees, and there's somehow in a hole here, and then the Gibraltar, the Atlas, Moroccan Atlas, the Apennines. So you see in the details, the nice east-west trend is now broken, much more complex. See the Western Alps, their trend is north-south, perpendicular to the east-west general trend. So that's not well oriented if you compare to north-south convergence. Shortening here is east-west, not north-south. Measured today with structures. So it tells you that there are some complexities and that crustal deformation is not, in these places, easily directly connected to plate kinematics. Calabria Apennines. It's also very odd in terms of orientation compared to the east-west trend. You see here these very rounded shapes. In terms of topography, that's the orogenic front marked by a thrust, but there are also places that are uplifted in the front. So the alpine topography is not only the zone of deformation by structures, it's also uplift of topography in the front. And there are also rifts in this area. Strange to find rifts in these places. Fallen basins at the front of the orogens. These yellow basins are fallen basins, but also large sac basins, basins that are with an axial of symmetry that is vertical, like the Paris Basin, that relates to some very big scale, lithospheric scale subsidence. Very, very big diversity of geological features. So how does it look like at depth? And this is thanks to seismic tomography. Everybody has seen seismic tomography. It's a very common way to retrieve lithospheric structure, looking at how the seismic wave propagate relative to an 1D model of reference. So we determine if waves are moving faster or slower. And this gives a map of blue when it's faster than the reference model, and red when it's slower. And geophysicists say that when it's blue, it's because it's stronger, colder, and thus resembles the lithosphere. And when it's red, it's where it's weaker and hotter, probably the asthenosphere. So these are map views. That it's a slice, horizontal slice at 200 kilometers, horizontal slice at 600 kilometers, and these are vertical slices in different places. So we can see at first order is here, there's huge difference between Eastern Europe and Western Europe. Here it's basically the Scandinavian craton. So it's a thick, rigid block, and it limits the Variscan and Alpine orogenies that didn't go beyond that. Then, when we look at 200 kilometers, we see red and blue. So if we try to follow the blue, there's blue here in the Betics, in the Gibraltar, blue in Calabria, somehow in Apennine, in the Alps, and then we have to move in the Carpathians and in the Aegean. But you see, this was used to identify the lithosphere. What is your analysis of this? Well, it says that lithosphere, if it's there, it's discontinuous on the horizontal view. You have plate here, no plate here, almost no plate here, a little bit of plate here, no plate here, and plate here. So it's discontinuous laterally. Strange. Let's look at the cross sections. That's the Calabrian slab, so it's a cross section like this. East-west. East-west, and the white spots are the hypocenters of earthquakes. So that's the Wadati-Benioff plain. So there's a good match between the red and blue difference and the Benioff plain. Actually, that's how they tuned their model. You see the color scheme here that is used is very important in the way we analyze the data, right? So the geophysicists, they play with that color scheme until they match the position of the earthquakes so that we could see, us geologists, we could see a lithosphere. Because we're happy to see the lithosphere. And they made the section exactly where the contrast is the biggest, where you have blue and red. They had made the section here, we'd see nothing. You see that, huh? 20 years ago, I told them, hey, I'm interested in these discontinuities, lateral discontinuities. Can we construct a 3D model of that? We're not sure of the data. They didn't want to play with that. So they just wanted to show the plates. Just did the section where you could see the plates. I just came back from EGU, it was last week. Well, now it's in there. 3D views of all this geophysical data, and it's very compelling because it's stimulating, and you don't see the plates. You see plates that have been deformed in all over the place. But, okay, let's go back to the basics. They just first wanted to show the plates, and you see one here that is plunging towards the west, and is kind of blocked in the mantle transition zones at about 600 kilometers, where it flattens. And the fact that there is a red zone here, they interpret it as being related to subduction first like this, and then retreat like that was blocked by the mantle transition zones. I think it makes sense. And the same in Gibraltar, except that it's plunging towards the east and then retreated towards the west. So you have things that went like that. Here in the north, that's illustrated by this section across the Carpathians. You have the Wadati-Benioff plain here, a blue zone that goes down towards the south and is also blocked in the transition zones by something like 600 kilometers. And that's also been interpreted as being related to subduction first like that and then retreat, which allows the asthenosphere to upwell in that region. And last section is across the Aegean. There you have a nice continuous blue anomaly that goes across the transition zones and even down to the core mantle boundary. So there the slab goes down. And it's also being retreated, and we'll see that again tomorrow. So at 600 kilometers, it's a good slice to show all the slab graveyard, all the place where all the slabs have been accumulating, except beneath Aegean, where the plate is going down. So in other words, in that system, you had 3 retreated slabs. 2 were plunging towards the north and then retreated towards the south, and 1 was plunging towards the south and retreated towards the north. So it's something like this, right? Well, one slab is much thicker than the others, but they go like this. You see? And what's the consequence of that? Well, above, in the upper plate, above the retreating slabs, you have opening of basins. And that starts to explain the much more complex situation in these zones. And the retreat of slab is not related to plate tectonics. It's not related to the plate motions far from the zone of deformation. We need to find another force for that. So it's probably one of the good candidates is probably the weight of the slab that starts to boom. And that's the time Africa started to converge rapidly and then slow down. So the slab first went fast and then slowed down, and start probably to weaken. And, that's my way to look at it. I wanted to show that 20 years ago with the geophysicists, they didn't want to go that way. But last week we discussed that and said, maybe there's some idea to that. We can go back. I'll send you my 3D model. That's my colleague in Italia that told me that. Okay, what about the slabs beneath the Himalaya Tibet? It's a bit more complex. So that's these are sections across. So that's one section. I'll take this one, north-south, and you see here south-north. That's the Himalayas are here, and that's Tibet here. And there's somehow a blue anomaly that goes down. So that's consistent with what we thought about the tectonics and geodynamics of India relative to Eurasia, with a subduction with a northward polarity. But then it looks like this anomaly is overturned. So the slab is like this. That's also not very well fitting with plate tectonics. Looks like the slab is folded by something that moves the plate faster than what it wants to do. Because if a slab is just falling down according to its buoyancy, it will go like this. If it's going like this, it's probably been pushed by something else that is adding something to the motion. Single overturned slab. And that was also, and we'll come back to that, was also one big surprise from these tomographic images, is to see each time only one slab. Surface geology find at least 1, 2, 3 sutures in some places. And the logic of plate tectonics was each ocean should be closed by one subduction zone, one slab. So 2 sutures, you should find 2 slabs. If there is only one slab for different oceans and different continental blocks, that means that they were part of the same plate. This idea of microplates is kind of not consistent with that. This is one single plate, which could have been oceanic for that part, continental for that part, oceanic for that part, continental for that part. Not sure, huh? But we'll come back to that. At least that's the observation. One slab, different sutures. And in that framework, we have this diversity with orogenic wedges, orogenic plateaus, intermountain basins. And we're going to now develop on that, starting with the first example, which is the Western Alps. Yeah. So we have, if you have questions now for the general scheme, now we're going to go into the details of the geology. It's okay for the general picture? Even for the bachelors? Yeah? You follow a bit, huh? I think for the bachelors, the idea is not to be able to grasp everything. Is to catch ideas, catch first order pictures, and then this will relate. The problem maybe is that you're going to ask too many questions to your teachers. You say, that's strange. We didn't see that with Prof. Van der Haag. Because teachers during the bachelors, I'm helping you, I'm trying to. During the bachelors, we know the idea is to give you something that works well, and is well defined with drawers where we put rocks, and structures that are well identified. But then, as we go further, we know it's not working that very well. So you have to be prepared for that. It doesn't mean that the basic that you're going to be taught is totally wrong, but it's the first order, and then you'll learn that it's not working everywhere. Okay? Okay, so the Western Alps. So that's this part of the topography. So that's Central Alps. We're not going to talk about it much at first, but just the Western Alps. Well, the cross-source scale structure was understood right from 100 years ago by Argan. He was ahead of his time. Swiss geologist, and this was allowed to be reconstructed because you see all these valleys going across, so they are natural cross-sections, and you see that these are folds, and these folds have axes that are either plunging towards the north or to the east, or to the south, sorry. So in other words, if you have one section across the structure here and you take the next valley, you can play with structural levels. So if it's plunging, let's say it's plunging towards the north, so this valley would be slightly lower structural level than this one, so it will allow to reconstruct the full geometry. That's how he managed to do that. He never went to 30 kilometers depth, but he could reconstruct that by extrapolating things from valley to valley. Wonderful structural analysis. And you see that didn't change. Huh? No, the next generations did the same work. It was a bit refined by seismic reflection data that I'm going to show, but basically it shows that we have foreland basins at the front, a cover that is decoupled from its basement in the fold and thrust belt, and then in the internal zone compared to the external. So first here, involvement of the basement in thrust from the foreland to the external zone. And then a contact here between the external zone and internal zone that marks the transition to high-grade nappes, metamorphic nappes, with overturned folds, polyphase folding, and so on. And here the transition from the Alpine belt to Adria, which is this zone. And these show the same things. That's the same shown in map. So we have the foreland basin, the fold and thrust belt, the internal crystalline massif, the external zone, the internal zone with crystalline massifs that are involved in the fold and thrust, and then the foreland in the other side. And all of these show that there is tectonic accretion of cluster units that are along a subduction zones that is heading towards the southeast. So that's a strange orientation relative to the convergence vector. So this is a map of all the seismic activity, current day seismic activity, with a guy that looked at even small seismic activity, very small. These are the magnitude. I think it's 4, 3, or 3, 4, no, 4, 3, 2, 1. And the surprise was that you see mostly thrust, I mean that's normal, right? Thrust in the front, but here, normal faults. And if you look at it in cross-section, thrust at the front, normal fault here. And that's the highest topography. That's Mont Blanc. Mont Blanc is 5,000 meters. So at first, that was a surprise. Now, how come in a zone of plate convergence, we have, at the same time, thrust at the front, normal faults in the internal zone? And as I said yesterday, well, the basic tectonics guy will say, okay, here is compression, and here is extension. Okay, we have to make a choice. Huh? Either the crust is thinning or thickening. Compression in the foreland and in external zone, extension in the interland, and strike slip zones in between, transfer zones. So we'll come back to that at the end. So in order to reconstruct the paleogeography, we rely on sedimentary sequences on rocks that have been hardly deformed, but we might still recognize carbonate sequence in the west, and then going to more sedimentary sequence that corresponds to oceanic sediments. So we have basically an European thin continental margin with small blocks separated by small rifts that are in transition with a larger ocean, which is called the Ligurian-Piedmont Ocean, that separates Europe from Gondwana. And this is one of the small alpine basins that formed during opening of the Central Atlantic. The crustal structure was refined after Argan by seismic data, deep seismic data, so we rely on the 3 sections. And we're going to concentrate on this one, which was the most resolved, the better one, the best one. And these ones are interesting, but it's more difficult to identify structures. So this one, that's the Ecorse profile. So we see fairly clearly here the moho. The moho at 30 kilometers depth, far from the Alps, and that deepens all the way to 55 kilometers beneath the Alps. So crust is thickened beneath the Alps. Well, that's consistent with isostasy and the topography. And then the internal structure. Well, what we see here is the cover, sedimentary cover, Mesozoic, compared to the basement, Variscan. There is a strong reflector here that marks the transition from cover to basement. And it's also that strong because there is a salt deposition during the Trias. And these are very good at forming reflectors. And you see at some places it thickens and thins, this reflector, and that corresponds to this harmonic deformation of that Trias salt deposit. And that favors the décollement of the cover, decoupling of the cover compared to the basement. So in the details, we find the thrust and fold belt here, structures. And starting from here, the basement looks like it's been offset as well. So here the faults are affecting the basement. That's consistent with what Argan had proposed, even though he couldn't see that. And the basement is here at the surface in the external crystalline massif. That's the Mont Blanc. And then you have this contact between external zone, internal zone, which is called the Penninic front in the Alps, and marks the transition from non-metamorphic rock of Alpine age to metamorphic rocks of Alpine age. And I just said that this today is a normal fault. But we know from geology that it was not a normal fault to start with, because we'll see that there is oceanic rocks here on top of continental rocks. So that's ophiolite. That's an abduction contact. So at some point it was a thrust. It's also metamorphic rocks on top of non-metamorphic rocks. So at some point it was a thrust. Right? You do not put metamorphic rocks on top of non-metamorphic rocks with a normal fault. Metamorphic rocks are not coming from the sky. They are coming from underneath. Right? So you were asking me how I do kinematics. That's how I do it. It's much more reliable. The big motion here is metamorphic rocks on top of non-metamorphic rocks. Maybe there is kinematic criteria here that that's the case actually. It tells you normal fault. That's the last hint. That's the last structure. It's not representative of the full deformation. So a kinematic criteria is nice, but you're not going to tell the full story with it. So here, what is also very surprising is that most reflectors, well, it's also inherent to the technique, which is seismic reflection, so you better catch the horizontal layers. It's not difficult to identify the vertical structures with that technique. Vertical structures are identified by breaks in the horizontal reflectors. But still, we see a lot of almost continuous horizontal reflectors. Well, look at the cake this morning. When it's shortened horizontally, you'd expect to have structures vertical. Structures are horizontal. So what is the shortening direction? Just vertical. Thank you, bachelors. No, I mean, advanced tectonics people still did not catch that in the Alps. The main structure here is horizontal. We're not going to get out of that. And it's shown in their structures, but they're still calling upon collision and indentation. No? Well, if I punch Europe in the face with Adria, it is not going to have this type of structures. That's for sure. So there is something else happening here. Yeah, and also one peculiar feature is that there is mantle at the surface, just at the contact between the Alps and Adria. So that's Italy. Huh? So that's also identified in geophysics, so we'll see that later. That's called the Ivrea body. And that's actually a very nice place to work for Variscan geology, because here you have the Variscan basement, so the basement that is all over Europe. So here it's only accessible in the external massif. It's also here, but it's very metamorphosed during alpine orogeny. But here it's been tilted from horizontal to vertical. So you can go across the Moho all the way to volcano. Really, it's 300 million years, so it has nothing to do with the Alps. Huh? Just do an apartheid. But it's, we're working here actually currently. Yeah? So we have dunites, pyroxenites, and then granulites, migmatites, granites, pluton into metasedentary rocks, and then volcanic rocks and sedimentary rocks all happened at 300 million years. So it's a picture of what happened on a vertical scale, poof, tilted on a horizontal scale. There's only few places in the world that you can see that. So, okay, everybody recognized the main structures, so the basement, Moho, and also there is here a layered lower crust, very seismically reflected lower crust that is found everywhere, here, there. It's more complex in here. So this everybody found, but then the discussion was, okay, what do we do with this internal zone? So here it was mantle, crust, repeated. That was the first interpretation in the 80s. Here, slightly more simple with mantle, crust, mantle, crust, mantle slices. Somehow equivalent. What I want to show here too is that, okay, feel free and be creative. You know, there are some places where people don't know. So I give that to master students. That's an exercise for master students. It's to reconstruct geologically and tectonically, geodynamically consistent section for the Alps, based on that and on the geology. So in other words, it's just not a matter to illustrate the finite state, but you have also to reconstruct a finite state that is consistent with the initial state that you can reconstruct. Here, only crust and then only one mantle. So that would be mantle here, and this is all crust, whereas for the others, there was mantle, crust. Same. And here it called upon Apulian mantle indenter. You see, this idea of Taponnier for the Indian indentation into Eurasia, I'm fighting here, fighting for geology, was so strong that these guys imagine horizontal indentation that would come to vertical indentation. And that explains the structures here, right? But this is the densest part of the lithosphere. It doesn't want to go up, it wants to go down. I think this is physically not really consistent.
So that can be attributed to the buoyancy or viscosity?
Sorry, with the air conditioning.
That upward movement, like you earlier said, like how the Deccan volcanism, it's due to viscosity, it stayed upwards. Now here the upward movement is due to which, buoyancy or viscosity?
I would say viscosity.
Viscosity.
Yeah. But here it's not magmatism. Huh? This is lithosphere. This is strong. It's not magmatism. Huh? It's strong, and it's why it's called to be indenting, because it's strong compared to the crust. That's the idea. It's not volcanism. Huh? Another one. Here it's a slightly different view, where Lardot tries to put a different metamorphic grade, which was not inferred. This was only referring here to paleogeographic. So crustal blocks, an ocean here, another crustal block, another ocean here, but no metamorphism. Metamorphism was not considered in these reconstructions. Here, for the first time, this guy said, okay, I'm going to put metamorphic grade. So the blue, it's blue schist. The purple is eclogite. And it's inferred eclogite facies at the bottom. And he's mentioning that because at the eclogite facies, crustal rocks look like mantle rocks in terms of geophysics. So basically, he says, okay, here you can do whatever you want. we're not able, with geophysics, we're not able to distinguish crustal and mantle rocks. Okay. So the nice thing about this guy's work was not only, I'm not too much in favor of his indenting model, but he made also a density model based on gravity. So this is the observed anomaly, and he modeled the anomaly, putting densities into his different blocks. So he managed to identify that here there is a 3.15 density zone that probably corresponds to mantle rocks. But it's difficult to distinguish between these and the 320, which might be eclogites, crustal rocks. So that's the oceanic ophiolite with 2.85. And you see that these are fairly sensitive. If it changes slightly the density, boom, it doesn't work. No, that's instead of 315, it takes 330 here, and it doesn't match. So these are very sensitive. And same here, if it changes the density of this, then boom, it doesn't match. It shows you the sensitivity of the model. So in terms of seismic tomography, so I reproduced here one of the crustal scale section and at the same scale as the tomography. So there is a fairly good match between that structure that is inferred from geology and seismic reflection, crustal scale, and the lithospheric scale where we see the blue zone going down with here a hole that is interpreted to be related to sort of boudinage at the lithospheric scale. So again, in cross-section we have here one suture, which is called the Valaisans suture, the Ligurian-Piemonte suture. So two sutures, two oceanic, separating one Eurasian margin, one crustal block, and another margin, continental margin here, in which is Gondwana. So two oceans, only one slab. What does that mean? That means that everything that is in here in the orogenic wedge comes from a single slab. These are crustal units that were probably partly entrained in depth with the subducting slab and then decoupled and formed the orogenic wedge, whether it was oceanic units or continental units. Oceanic units, continental units. They are all coming from the same slab. That's something very important in the reconstructions. It's not because you have one suture that you have one slab. You might have several sutures and one slab. So that's been confirmed by more recent seismic tomography, where you see this single slab, and that is followed much further down into the mantle. So in terms of geology, so we first going to go from the foreland to the interland. We start with the foreland with Mesozoic sedimentary cover decoupled from the Variscan basement. Variscan basement that is here exhumed in the external crystalline massif and shown here, and its cover is here. So now we move to the internal zone where we have also crystalline basement here and its cover, which is here. That's the cover, and the crystalline basement is forming here, the internal massif. And the third paleogeographic domain is the Ligurian Piemonte Ocean, or the Alpine Ocean, which is on top of that sequence and corresponds to oceanic sediments and oceanic rocks. So let's start from the external zone. So we see here the sedimentary cover detached from its basement with thrust and fold, typical fold and thrust belt. You see the structures that you can see in the field. In the foreland is also the foreland basin. That is a depression at the front of the orogen that is caused by loading of the plate. And as the plate is loaded, is subsiding, and it receives all the sediments coming from erosion of the belt. coarse sediments, conglomerates and sandstones. So that's another example. We find that in the northern part, but you find that also on the southern part along the Alpine arc. It's folded here. It's also involved in the thrust and folds, and you can see that here. And that's a place here where you have the carbonate Mesozoic sequence that is thrusting on top of the conglomerates of Cenozoic age. And that's seen in the field. So these are the type of structures that you can see then in the more eastern part of the external zone, with a strong control of the carbonate limestone layers on the morphology. And there are two big limestone. One is Jurassic. It's called the Titonian, and the other one is Urgonian. It's Cretaceous. And these control the morphology, and it allows to follow the structure in the scenery. So at first, the folds are slightly inclined, the fold axis and axial plane. But then as we move towards the internal zone, then these folds tend to be lying with axial planes that are more inclined, even sometimes horizontal. And you can see here the contact between this cover and its basement. So it looks like it's been detached from the basement. And how much of that is related to plate tectonics? How much of that is just gravity sliding off a place that is uplifted? Difficult. The debate is open. What is compelling is that most of this motion, dated by the activity of faults, is after the main phase of convergence. So it's tempting to say that most of it is post-convergence. So it's not related directly to plate tectonics, but more to gravity readjustment of the structure after thickening of the crust. I will come back to that. That's the Mont Blanc, so that's here. And you see the structures in, that's these here are these. You see the overturned folds. And repeated Urgonian limestone. So that's the nappe that goes over the crystalline basement. That's called the Morcle nappe. It's a famous structure in the Swiss Alps. And at first, when you look at these, you think, okay, well, the guy, it's a bit crazy, It was easy going with this. No, this is seen in the scenery. You can see these folds exactly, and that was what Argan was doing that precisely. And there's no more precise geology than in the Swiss Alps. You can trust the Swiss, They do maps at the 1/200 meter scale. They map all outcrops, every outcrop, very precisely. So this is the best known place for geology on Earth. And then we move to the internal zone with the ophiolite, the Ligurian domain, with the Mont Viso. And Mont Viso is this thing here. You can see it is a block of eclogite. And here you see block of gabbros, basalts, metasediments, radiolarite, cherts, calc-schist, and pillows that are preserved. So it's a typical ophiolite. So now let's look at the external internal zone structure, transition from external to internal zones with the external crystalline massif and then the internal crystalline massif. And the structure is really sort of a fan structure with structures dipping towards the east in the west and then a turn where structures are dipping towards the west in the east. That's a main feature of the Alps, and people have invoked thrusting for this and then back thrusting for the other ones, whatever it means. But in this proposition of Gidon, you can start to get a hint that, okay, maybe part of that might be also related to folding several times, and that repetition might be related to isoclinal fold. And really, so that's the ophiolite. If you follow the ophiolite, it's as a clip here, but goes down here, is here, but goes again above the crystalline basement and is rooted here. So the suture is here. And it's been going above the continent and then several times as clippers. And this is consistent with the metamorphic grade, going from low grade metamorphic to higher grade, from external zone to internal zone. And that corresponds to high pressure, low temperature metamorphic gradient, with green schist facies, blue schist facies, eclogites, and even ultra high pressures in these rocks. So let's look at it in some details, because I had some question about detailed maps and structures. So that's a section across that internal zone from the Pennic front that marks transition from no metamorphism to alpine metamorphism all the way to this internal crystalline massif, or Dora Mera. And we go across first a series of metasediments, green schist facies, folded, refolded, with PT conditions 4-5 kilobars, 300 degrees. Then as we move eastward, the PT conditions increase, mostly in pressure, not so much in temperature, reaching 12-15 kilobars. That's in the blue schist, eclogite facies. And at Dora Mera, this internal crystalline massif, has recorded even ultra high pressure, with pressure going up to 24 kilobars with coesite. That's what it looks like in the field. So I'm not sure you can see it very well here, but you have isoclinal folds that are folded, refolded. That's F1, F2. And that's the same here. F1 refolded by F2. Maybe I can draw that. No.
Oliver, do you need a pen or something?
No, but it's okay. It's okay. It was just for structures, but F1, F2, that's maybe going a bit too far for bachelors, but for the others, it's okay, right? Are you okay with F1, F2? Huh? So it means that the rocks has been folded once and then twice. So you have the first fold indices that has been refolded by another one. And you see that in the field. That's an F1. If you follow that layer, it goes like this, it turns. That's the isoclinal hinge F1 that is refolded by F2. And the F2s are asymmetric. And you see that at the regional scale, F1 refolded by F2. So that's one of the basic principles of structural geology, is that the things that you see at the outcrop scale, it's fractal. And you can see them at regional scale and even at microscopic scale. And we hope it works. If not, no, we're in trouble. I was asked about retrogression. So the way to do it is to sample. To sample here, you see my hand, I sample that, and sample here to have the minerals that are in equilibrium with the F1 structures and the ones that are in equilibrium with the F2. There actually is also an F3 here in this region. And this is a representative of the S2, the schistosity 2, and the schistosity 3. And you see the minerals are not the same. You have blue minerals that underline the folded foliation, that S2. That's glaucophane. That's typical blue schist facies mineral, high pressure. And in the axial plane of the F3 fold, you have chlorite retrogression. So there's retrogression of glaucophane plus other minerals, and I don't give you the full reaction, into chlorite, which is a lower grade. So that means that the rock, when it was folded, went from higher grade to lower grade conditions. So playing with these mineral assemblages correlated to the structures, putting in the section, I was asked how many samples I need. Well, I need the good ones first. Take the good ones that allow you to see the different structures and relate the different structures to different mineral paragenesis, and then put them into a framework that is consistent at the scale which is consistent for the problem that you want to solve. Okay, so these then were put into a PT diagram, which each of these boxes represents one sample of that section. So we have different conditions recorded from the external zones to the low-grade zone to the high-grade zone. And these PT can be compared to temperature time. And temperature time that can be retrieved from dating rocks. And we can date rocks with different type of what we call thermochronometers, minerals that will catch the time at some temperature. I'll take, for example, mica, biotite, black mica. It has a lot of potassium. And potassium decays into argon. Argon is a noble gas. It doesn't combine to anything. It wants to live its free life. But at high temperature, the potassium that will disintegrate into argon will not be trapped in between the foliae of the micas, because the foliae are kind of far away from each other. So the argon can go out. But that's a temperature estimated to be 350 degrees. These foliae will be closer to each other, and the argon is trapped. That's the time at which the clock starts. We can count then all the potassium and all the argon that is in the rock, and we get the potassium-argon age, which represents the time at which the rock, biotite, passed below 300 degrees, 350 degrees. And we can do that with Ansible, we can do that with other type of thermochronometers, and that will give us all the story from 600, that's 2, 4, 6. That's from the 700 degrees to all the way to 100 degrees. So we have a temperature time path. And you can do that for the different zones. The Ramera, the crystalline massif, the Montviso, and the schist lustré of the Briançonnais. And you see they have different stories. And if you combine pressure, temperature, and temperature time, you see that temperature is common, so you can cancel that, and reconstruct something which is artificial, which is a pressure time path. And pressure time tells you about burial exhumation history. And what do we see here? We see two periods. So that's pressure, and we can transform pressure in depth, burial depth, so that's 100 kilometers for 30 kilobars. And you see that all these units went down pressure, we're recording decompression, before 30 million years. And that corresponds to rapid exhumation. These rocks went fast back to the surface. And that's at the surface at a depth which is close to 5 kilometers. And then the last exhumation was slow, from 30 to today, and that's the last 5 kilometers. So 2 periods, remember that? Rapid, slow. And what is impressive, if Dora Meira, you see it was the deepest and exhumed the latest. Dora Meira, that's here. That's the one that is the further east. And that's the one that was the deepest and came back the fastest and the latest. So we have to take that into account in our model. And if you take the age of exhumation of Dora Meira to be 30 million years, and consider how fast it was required, the velocity was required to take it down to 100 kilometers, then you can say maybe it took 20 million years at a conversion speed of a few centimeters per year. And that gives us the timing of onset of burial of about 50 million years. And exhumation between 35 and 30 million years for this Dora Mera unit. So I'll skip that, and I'll insist on that. So that's the same thing. I insist on that 30 million years. So what happened at 30 million years, before and after, in the Foreland Basin here? Well, what could be the exhumation process? What could allow rocks to be back to the surface? What do you have in store? Uplift. Uplift defines the motion of the surface. It doesn't. So that's very. Thank you for your question. Allows me to make definitions. Do you have a pen actually for? Make sure because from now we need to be precise in the terminology. So we take 0 as being C. Uplift is motion of the Earth's surface relative to that reference frame, to an external one. The contrary is subsidence. What is exhumation? Exhumation is motion of a point, material point, relative to the topographic surface, not the sea. Exhumation is getting closer to the surface. And burial is the contrary. So uplift and subsidence, you gain mostly from sedimentary record, whether it's above sea level or below sea level. Was the surface above or below sea level? Exhumation and burial you get from metamorphic rocks, pressure, temperature. Does that clarify? So what are the mechanisms that allow rocks to go from deep in the earth to the surface? Thrusting. Ah, interesting one too. So what? So that's a cross section, 0, 30 kilometers. And you have a thrust. What's the consequence of that? A thrust at a crossal scale, followed by isostatic compensation, will result in uplift of the surface, crossal thickening, so compression for the tectonics. What about material points? Take A here relative to B, that were the same depth to start with. A is now here, and B is here. And if there was no other thing than just the thrust and isostatic compensation, the distance from the surface of A didn't change. No exhumation. Uplift without exhumation. The only thing that happens is burial of B. It's further to the surface, so thrusting causes burial. But then there is a stretch in the reasoning that most tectonics people that work on the upper crust, they say uplift is related to erosion. And that is a process of exhumation. But then they forget most of the time that there is one step before. It's thickening, isostatic rebound, and then erosion. So uplift is followed by exhumation. It's not thrusting exhumation. Right? Is it more clear? So erosion is one first process of exhumation. Do you have other things in store? Rifting, normal faulting. If you have normal faults, a normal fault will cause exhumation of the footwall. Okay, so let's test first erosion on the alpine example. So we'd expect, because most of the exhumation is occurring before 30 million years, to have lots of sediments before 30 million years in the Foreland Basin, right? So we looked at that. And in the Foreland Basin, so that's the progression of the position of the Foreland Basin in this zone, according to geology. And before 33.7 million years, actually, it's all the blue, and after it's all the pink. Before it's marine sediments, in what we call starved basins, so basins with turbidites that are not filled up. So it's not a lot of sediments, but below sea level. And most of the sediments come after 33 million years. So that's the flysch of Dewey that I told yesterday, and that's the molasse. And it's after 33 million years in continental basins that are overfilled. Sediments go over the basin, they go all over the place because there's no space. So in other words, most of the exhumation, most of the erosion occurred at the end of the story, after 33. It's not exactly 30, but it's 33. And before 33, it was not so much erosion, and the topography was low, sea level. So if we turn the reasoning around, it means that this exhumation did not occur by erosion. Most of it occurred with another mechanism. Will rifting be pertinent? Well, we are in a zone of plate convergence, crustal thickening. We're not really looking for rifting here. But we see that there's something to that. So I do the mass balance. I'm going to skip that. So here's the model we can propose for that. So a first stage of conversions accommodated by oceanic subduction, some tectonic accretion of units here, the schist lustré Montviso, the Briançonnet continental rise is being subducted as well. And you have here the eclogite starts to be, that the peak metamorphism recorded at 50 million years. And then these units that were buried start to go up, being exhumed in the same kinematic framework. And at first it starts with below sea level, and above sea level is only at the end of the history. So that's the same story here with fast convergence before 30 million years, which results in burial associated with oceanic subduction and then continental subduction, and then tectonic units that start to be decoupled from the downgoing slab, whether they are oceanic or continental, and which makes these naps. And you see here I added an half arrow, which corresponds to, it's not rifting, but it's what we would call here a normal fault. This block moves down compared to this block. A normal fault in the middle of the mountain belt. So I would call that, not really, I mean, it's a normal fault or extensional shear zone, as we call that, but it's an extensional shear zone that contributes to construction of the orogenic belt. It's not thinning the crust. It's allowing for exhumation of the buried units. So it's a constructive extensional shear zone. It's not destructive in terms of... So be careful, just doing kinematics will lead you to wrong conclusions in that case. Say, extension, crustal thinning. No, it's contemporaneous to thickening of the crust.
Is that type of exhumation is called abduction, or is it something different?
No, because the abduction is here. The abduction is here. But it's so you have, in other words, you have a thrust here and a normal fault here that are contemporaneous. And that allows for abduction. Somehow. Yeah. Yeah, I'm not going into the details, but you have actually here two different types of ophiolites. You have the ophiolite that has gone into depth, this one, but at the surface there's also an ophiolite here that's somehow represented here that never got buried. And it's where the pillow lavas are fully preserved. It's on top here, that's probably the same ocean, but it's been preserved here at the top. So that's real abduction. Okay, and one way to favor decoupling of these units that have been first entrained with subduction and are here at that time, and then decouple, is to have retreat. Because if you have retreat, slab retreat, you see my two hands are connected, and if there's retreat, there's a hole here. And the buoyant units, they want to go back and might fill up this hole. And that's the vertical exhumation. And that's what is related to normal fault on one side and thrust fault on the other side. See these units? Normal fault here, thrust fault here. And that's here associated with retreat. Do we have other evidences for retreat in that region? Or either I stop here, I think that's it, yeah. Well, there are some other evidence with seismic anisotropy which measure the orientation of olivine minerals in the mantle. And it shows sort of the orientation of olivine that goes around, that's the alpine arc here. And you see the olivine minerals, the stretching initiation in the mantle is going around the arc. And the idea is that this slab, as it retreats, the mantle will flow around as a toroidal flow around the retreating slab. And this might be recorded by that. This is geopoesy, but it's kind of exciting. So, okay, I wanted to finish with that. So I think the main message is here. The succession of continental subduction, decoupling, exhumation, and then erosion with topographic uplift. And for tomorrow, I'll leave you with that question. Okay, we dealt with the high pressure, low temperature gradient in here. And that is explained by the model I proposed to you. Now, what happens here? In the central hub, instead of having a geothermal gradient of 10 degrees per kilometer, associated with high pressure, low temperature, we have a geothermal gradient of 40 degrees per kilometer recorded by metamorphic rocks. So it's mid-pressure, mid-temperature rocks. Nothing to do with the Western Alps. How do we go from one to the other? That's the next step in our journey. Will be dealt with tomorrow. Going from low geotherm to high geotherm. Going from wedge to orogenic plateau. How long it takes for the crust to heat up was one question yesterday. How long it takes to generate migmatites. Huh? Yeah. So we'll see that tomorrow. Okay, are you about with me? Following somehow? The big lines? Okay. Questions?
Regarding the exhumations which you explained here, I don't get why the A part is not moving up. Like, A will also get exhumed.
It's moving up relative to the sea. But it's not moving up relative to the surface. If I take my middle finger, put it on top, there's still the same number of fingers on top. But it's been uplifted. Why? If I want to exhume, I need to remove fingers on top. That's a good way to show it, no? Well, I thank you for your attention. And again, I think you want to also be careful because I'm getting older. I'm terribly biased in my way of showing things. So try to make the distinguish what is the data, what is the model. And of course, as a researcher, I want to show the model that I proposed in the best way I can. But there might be flaws, and this is what you want to identify. Might be difficult for bachelor students, but at the master level or doctoral level, you can start, okay, I didn't understand that. And usually when you say that to yourself, at first thing you think, oh, it's probably because I'm stupid. No. There's no reason why you should be more stupid than I am or the other way around. No, there's no reason that I should be more stupid than you. We are all human beings with brains and we can think, we can make observations. So if you didn't understand correctly, that's probably that I didn't explain correctly, and that's probably because I didn't understand it correctly. And that's where the future research is. That's something also you need to catch from these lectures. Is okay, this seems to make sense, but this, maybe that's a place for future research. Okay? So if you no further questions, we can see each other tomorrow. But I'm available also if somebody wants to talk, present his projects or long-term project for bachelor's or master doctoral students. I'm available. Just let me know. It's just today is Tuesday. Tomorrow I have appointment at after the lectures, but this afternoon I'm okay. Thursday we have the general conference, so it's probably today or tomorrow is the best call if you want to discuss.
Any questions?
So you said 2 of the line sequences.
Yeah.
Do you see any?
So can you please, we can't hear you, sir. So
Yeah, I'm asking about the ophiolite sequences.
Different ophiolites, yeah.
Two different sequences. So what is the difference in the sequence?
Yeah, I didn't really insist too much on that, but in that map there are 3 different things in terms of ophiolites. There is here a first green unit that is called the Valaisans. Valaisans is also some kind of oceanic rocks that are in the green schist facies to starting to blue schist. So that's the first one. And then you have continental sediments, and then again oceanic sediments in dark blue with eclogites in the deep blue. And that's the Liguro-Piemontese Ocean. And then part of that ophiolite is also, I'm not sure it's there, but it's probably somewhere here. It's a low-grade unit that is on top of it's a clip on top of the continental units. So there are really 3 different things. Green schist facies, blue schist oceanic rocks, eclogite facies oceanic rocks, and low-grade oceanic rocks on top. So this is probably reflecting 2 different small oceans, especially this one might be very small, as it thins towards the south. And that's in the tectonic reconstructions. That's not shown here, but it's possible that in between this Briançonnais and the European margin, there was another rift here, maybe going all the way to oceanic domain. And then this will close afterwards. So the first ocean will close with the part that will remain on top without being really metamorphosed, and the rest would be going down. So this part is there, never been buried, and the rest is there, been buried. And this part is here, never been buried. This part has been exhumed, and boom, this part slides on top towards the foreland. I just didn't represent here in that reconstruction the Western Ocean that might have been here. Would that answer your question somehow? In the sequence. It's mostly gabbros, basalts, and cherts. And
Be the same in both the cases?
no, the age of the Valaisans and Liguro-Piemontese is not the same age of the gabbro. Is I think Jurassic in the Liguro-Piemontese and Cretaceous.
Asking about some ophiolite sequence you find plagio-granite.
Okay. This I don't know. This I don't know. I don't think there's plagiogranite in the low-grade sequence. Yes, there in the clip there is plagiogranite actually. Yeah, for the one that went to blue schist and eclogite, I'm not sure people have identified plagiogranite. It's possible, but it's all very deformed. You can imagine it's been folded, refolded, refolded.
And about the normal fault
Yes.
in
Yes.
right hand.
This one.
Yeah. So let's say to explain the one of the plate is passive.
Yes.
What is the rate of
Exactly. That's good point. I mean, this Adria, it's made of the same rocks of Variscan basement as the one of Briançonnais and European margin. And it's not been deformed. Almost not been deformed. It's passive. So I think it's another evidence against an indenter. Because the indenter, if it's made of the same rocks with roughly the same thermal history, should be with the same strength on both sides. So they should be deformed on both sides. So the fact that it's not deformed is telling me that here building of this orogenic wedge is mostly by burial exhumation, with this not playing much a role. Except that it's being the upper plate below which rocks were buried and exhumed. So it's a way to construct an orogeny belt without collision. Shocking. It's orogenic wedge construction without collision. If it was not for, I mean, there's only a few places where units of that are on top of the oceanic realm. And here barely the two continents are one on top of each other. And they're not really in contact with each other. So it's not really collision. It's burial exhumation. And the rock units that form, that's a very good question. So the rock units that form the orogenic belt, where do they come from? From the upper plate or the lower plate? These units, do they come from here or from there? They come from the lower plate. They are today on the upper plate relative to that thrust, but they come from the lower plate. They do not come from the upper plate. Very important to keep that in mind for the next examples. So it's a transfer of units from lower plate to upper plate without collision. Okay, very good questions. Thank you, because it helps clarifying, I think. Last one? No. I thought you were. So see you tomorrow then.
Is your time?